Hello, everyone. Today I want to discuss the end-to-end machine learning project. Here, I want to give you an introduction on what are the major steps for machine learning project. So when you work through your course project, you should think through all of these steps as well and work through these steps on your own. And then when you come back to a real business world, when you start working on specific machine learning project, you should always kind of follow some of these steps and think through some of these key thinking points. So here is the list. Number one, look at the big picture. Number two, get the data. Number three, discover and visualize the data to gain insights. Number four, prepare the data for machine learning algorithms. Number five, select a model and train it. Number six, fine-tune your model. Number seven, present your solution. Number eight, launch, monitor, and maintain your system. So you see that this is really the end-to-end process, starting from thinking about where, how your problem sits in the whole organization, all the way through until you finalize your model and then try to put the model into production. And with continuous monitoring process to further enhance down the road. So this is a whole end-to-end processes for machine learning project. We're going to discuss all of this in detail one by one, and then I would also spend some time to give you some tips on how to look through some of the code that come along with the textbook. Okay. First thing that I want to mention is just to give you some tips on where you can find some of the real world data. So here I put them into four categories, which also kind of followed what the textbook mentioned. The first three categories coming from the textbook. If you look at the first category, it's called popular open data repositories. If you ever come across any data related project, you probably have already explored some of these links one way or the other. So the first one is UC Irvine Machine Learning Repository. You should take a look. Actually, I'm going to show you after I go through all of this list. And then it has a lot of open data repository, and a lot of the data is already well cleaned. So for some of the real world problem, you probably don't want to start with this just because a lot of cleaning is already done. A lot of practices are already done on the data. That's why it's very clean data set that can help you to run some of the algorithms for sure. It's missing the cleaning data as a step for machine learning practice purposes. Number two, Kaggle dataset. This is probably not new for all of you. You should see that in Kaggle there's a bunch of different datasets that you can experiment on. And Amazon AWS dataset, you could go there and take a look as well. And these three links gives you Metaportals, the list open data repositories. Apparently, for example, UC Irvine would be one of the in one of these data portal. So you should go there and potentially find some data that interests you. And also some other pages listing many popular open data repositories, such as Wikipedia list of machine learning datasets, Quora.com questions, dataset subreddit, and that's the three categories. In addition, I think you should also go to these three sites that include general economy, financials, demographics, and NYC open data. The first two, the first one, the last one is census and fresh solutions that includes economy and financials. The one in the middle, open data.cityofnewyork.us, has NYC open data. So you should go there. I can quickly show you some of these links. You can see here, this UCF1, it has a lot of data. For example, IRIS data itself is a famous data set that you can leverage, some others as well. This is from Kaggle, all kinds of data that you can search for if you're interested in. This is open data from AWS. Go through all of this on your own and at least get a sense on what's out there. This is data portals, open data from EU for coming from different country and number of data sets. Quad open data like stock prices, all kinds of like auto sales estimates, company spending and payment patterns, etc. And this is Wikipedia, a bunch of different data. Quora questions, where can I find large data sets open to public? Reddit. And of course, I actually don't have the other three that are open, but you get the idea. So just go ahead and look at all of this data set. And then you should be selecting one of the data set for your home cost project. Not necessarily from this list, but at least here is just giving you some directions that you can look into. First step, let's look at the big picture. So in this example, we're trying to analyze California housing prices. So this is coming from 1990 census data, which is 30 years ago. It has population, median income, median housing prices, etc. for each census block group. And you can see that from the data, the price was still around most expensive ones is around 300,000, which is apparently much less than today's California house prices. So at least this is a full data set that could help you to run through some of the machine learning algorithms. So look at the big picture. What you want to see is, where do I stand in the whole organization pipeline? Where do I stand, meaning where do this problem stands? Where do this problem stand in the whole organization? See, for example, if you look at this problem that you're trying to price the predict the house price, where it really stands is it's actually most likely have some sort of upstream components, have some district data, and then you need to predict the home price, and so that you can predict the district price, and then with other signals together, you might want to make a decision for the business to see whether you want to make an investment on specific pocket of the state. And then at the end, you would make an investment decision. So apparently, looks like this price prediction is really one of the key components for the investment decision. With that being said, you should be aware how accurate your price prediction is and how generalizable your price prediction engine is down the road so that you make sure it's going to work in the whole business system. And then here are some questions that you should be asking yourself, such as what would be the objective, what's the status quo for the problem, and then you start designing your problem, phrase your problem, frame your problem, think about, is this going to be a supervised or unsupervised or reinforcement learning, or is this going to be a regression or multiple regression or decision trees or random forest or some other machine learning algorithms that you want to test on. Before you do that, you have to really select a performance metric. And these are the two key ones that potentially you can use. But this doesn't mean those are the only tools. So one of them is called root mean squared error. So it's simple. Basically it says you have a function that to predict based on a bunch of x input to predict a corresponding y minus the actual y value. This is yi, the actual y value, and this is predicted y value, and the difference squared, and sum all of them for all of the observations times 1 over n number of observations, and take the square root. So this is called root mean squared error. Another metric that you can use is called mean absolute error. So it's the same thing, except that instead of using squared, here we use absolute value and summation times 1 over m. So this is called MAE, the other one called root RMSE. These are the metrics you could use for a lot of machine learning algorithms, and you will see in a lot of the follow-up discussion, like all the support vector machines, random forest would be leveraging some of this metric. It is always a good practice to list and verify the assumptions that we made so far, such as, what's your assumptions would be things like maybe I kind of assume that some of the variables that we don't know would have no impact on the potential problem that we're trying to solve. For example, for this housing prices. So you should always think about, did I make any assumption here? Should I go back and revise some of the assumptions? Now, after we frame the business problem, you kind of know where this problem stands, and then you should start thinking, where can I get the data? In real business setting, you would think about, okay, maybe I need to reach out to different departments to get different data, and then I need to put them together. In this example, you can see that if you go back to this link, which shows the full Juniper notebook that's available for the textbook, go into that link, download the whole thing, and then we could look into each one of the Juniper notebook one by one. Okay, you can also set up your environment photos through page 45 to 48 of the textbook. By now, I assume you already have an environment to work with. The way that one way that you could do would be just go to Anaconda Navigator and install Anaconda Navigator, which already comes with PyCharm, Jupyter, iStudio, Spider, etc., and then you can leverage Jupyter there. It's probably easier to just go to Anaconda Navigator. Then you could download the data you could have two ways. One way you could just use a fetch function, fetch housing data, and fetch the data. The other way would be download the entire Git repository and put it into your working directory, and then just revise some of the code and try to read through your own disk rather than go through the internet. I think this one, download the entire Git repository, probably would save some effort in terms of the running time. So once you have the data in your environment, you want to take a quick look at the data structure. This is always something that you want to do, not in any of the data analysis or statistics or machine learning project. You can look at the data using df.head. It's equivalent to head df in R to look at the first couple rows in the data frame, df.info to get a quick description of the data, and pay attention to the missing data on some of the dimensions after you run through the df.info. And you could also look at df column dot value underscore counts to see the categorical variable distribution. So what is categorical variable? That would be something qualitative instead of a numeric variable. And you could use df.describe to see the summary statistics for the numerical variables, which is equivalent to what we saw just now for the value underscore counts for categorical variables. df.hist to see the histogram of the data. This is just really give you a sense on what are the key commands that you might be using to look at the data structure. After that, you want to think through, I may need to create a test set. So if you have never come across with this concept of test sets, I want you to go through the link that I have here on the slide, but here I'll give you a brief introduction. So what is a test set? Why do we need that? Let's look at the chart. So this chart on the x-axis is model complexity, and the y-axis is error. So what we're suggesting is, let's look at the red line. As the model becomes more complex, the error becomes smaller. So in other words, you can start with something simple. You have a lot of error in your model and keeps making your model more and more and more and more complex. And as time goes on, you would improve the model's prediction error, which would make the error smaller, which is this red line represent. However, when your model becomes very complex, now you want to apply your model to something else. Something else that's what we call it unseen data, a different sample of the original population, and then you want to apply to that. There is a chance that if your model becomes more complex, you cannot, when you apply onto a different model, it's not doing well, which is this blue line represent. So as model becomes more complex, your model cannot be applied to some other similar data sets coming from different samples of the population. Now that's called variance becomes bigger. So as your model becomes more complex, variance becomes bigger. Meanwhile, bias becomes smaller. Error is small. So this situation, we call it as lack of generalizability. meaning you cannot easily generalize your model to something unseen data. So that's lack of generalizability. So you have to think through how you want to make sure your model is doing well on what you see, and also is doing well on what you haven't seen. That's the reason we want to minimize this black line, which is optimum model complexity. And this black line is a combination of bias plus bias squared plus the variance. So it's a trade-off between model complexity and generalizability of your model. So once you have that, you want to pick the minimized total error for the model, so that you would you would know that your model not only doing reasonably well on your data that you see, but also would do reasonably well on other data that you have never seen. Okay, so that's the whole purpose of create a test set. So you use the training data to run through your model and use your test data to test how well the model is doing. So you can see that in the textbook, it says you can do random sampling from so that you say, okay, I can use 70% of my data being the training data, the other 30% as a test data, and sometimes people use 80% as training, 20% as test. You could also potentially use 90% as training and 10% as test. It really depends on your own on your own preference, and also this depends on how big your data is. Whether you only need 70%, you already have a lot of observations to run through your training model. Some people even suggest 50% as a training data set. And then there's a chance that just because this is random sampling, there's a chance that next time when you come back, you realize, oh, my test set changed. So you really don't want to do that, just because you want to make sure that you would be able to replicate your results, right? So that's why potential solutions of doing that would be three major ways. Number one, you can save the test data, you can reuse it. Number two, you could set a random number generator seed to help you to kind of fix the random sampling sequence, so that next time when you come back, you pick the same set of the samples. The third approach would be add an identifier to the data, just like an index, so that you know which one is picked. So think about it, just the index, and in the index, it is train or test, and you could always just pick the test set down the road. And in scikit-learn, you could use train underscore test underscore split to get the test set, and you can also leverage random underscore state in the function. Another different way is called stratified sampling. So if you haven't heard of this term, let's take a look, right? The population is divided into homogeneous subgroups that's called strata. It's divided into different groups, right? That's the first concept. And then the right number of incidences is sampled from each stratum to guarantee that the test set is representative of the overall population. Let's just take an example. Suppose you chatted with expert in your company who told you that the median income is a very important attribute to predict the median housing prices, which most likely makes sense. And then you may want to ensure that the test set is representative of the various categories of incomes in the whole data set. Let's use this as an example. For example, if you look at the histogram of the income, first of all, right, when you did those data exploration earlier, you should actually know what kind of level that we're working with for different variable or predictors. For this example, if you look at the income category as being a variable, looking at the housing, the income, right? You can see that in this category, which stands for 10,000. Okay, 10,000. You should actually know your data. Means 1.0 is 10,000, and this is a distribution histogram, less than 1,000 observations in the data. And then for 20,000, somewhere around 20,000, it's more than 6,000. So when you do that stratified sampling, you want to leverage these categories to make sure in your test sample, it's still representative, meaning if this only accounts for 5% of whole categories, all the categories, you should still only get 5% in your test data for this particular category. So that's called stratified sampling. Again, you want to make sure in your sample, the percentage for each category is the same as what you see in the whole data set. And then the different categories essentially is the strata that we just discussed. We want to make sure that in the sample, that percentage for this strata is the same as what is in the whole data set. Or you consider that whole data set is your population. Okay, that's another way. After that, we comes to the third step called discover and visualize the data to gain insights. So you could just draw a scatter plot to look at based on longitude and latitude where all those observations. You could even add the median house income value, median house value to be your to represent different colors, so that you kind of see that, okay, here is more expensive. Those two areas are more expensive than the rest of the area, which would be San Francisco area and Los Angeles area. And you want to do some simple analysis such as correlation coefficients to look at which one is more correlated with my house price, median income, total rooms, and house median age looks like more positive correlated to the house value. And you can also see this latitude, longitude probably represents some sort of location that negatively correlated with the housing price. Even it's small, but still somewhat negatively correlated. Here, it just give you some example what is correlation coefficients. You kind of probably know this would represent +1, and some of this would be positive and close to 0, just random, negative, -0.8, -1, and then a lot of this just shows no correlation at all. Once you draw the scatter plot, you could also look at scatter matrix. So what it tells you is And the diagonals would be the histogram of each variable that we're investigating. And off diagonals would be the correlation scatter plot between, for example, use this as an example, median house value versus median income. Apparently it's positive, right? And then you can see that median income and house median age doesn't look like there's any sort of relationship. Well, you should go through this process on your own as well. Potentially, you could also experiment on some other derived variables. Here, I give you an example. Maybe you want to introduce a variable called bedrooms per room. So you use all the number of bedrooms divided by total rooms in the data set so that you come back with bedrooms per room. Oh, it turns out it actually have a big negative correlation with house price. That's something you want always to explore. And you might be questioning what would be the proper way to come up. It really depends on your knowledge of the data set and the business knowledge of different predictors. And here for number 4, it's called prepare the data for machine learning algorithm. Basically what it does is just trying to automate some data preparation. As you know, if it's going to be something that you're going to use repeatedly down the road, then you probably want to do this. But if you're going to just one-time prototype, you may not going to do this at all. Let's just think, right? Let's just assume this is going to be a project that you're going to reuse your algorithm down the road. So what you can do is you would automate the data preparation. It made it easier for you to experiment on different variables if you want to do all kinds of transformation. So it essentially says you will build a library of transformation functions so that you can reuse in future projects. I also want to mention the data cleaning step, which is essential for the data preparation. So let's think about the first one. What if you have missing values? You can do a couple of things. You could drop the missing values. You could potentially just drop the variable rather than only those observations. You could also think about using median or mean of that variable to fill those NA. You could potentially infer from other variables as well if you know there's some other relationship which exists in the data. So that would be for data cleaning for missing values. How about text and categorical attributes of variables? You want to potentially to create some sort of dummy variable. For example, ocean proximity. It may have less than 1 hour to ocean, maybe near bay, maybe inland. You know, the inland is not going to be close to the ocean, but less than 1 hour ocean versus near bay and maybe some other things, 10 minutes walk to the ocean would be something that you consider to be very, very close to ocean. So you should group some of those variables together so that you can create dummy variables for your categorical variable. And you want to automate the process of defining new variables as we discussed earlier. You potentially want to do something called feature scaling. One way would be called min-max scaling, which is also called normalization. So what you do is you rescale so that the value ranging from 0 to 1. So basically what you can do is you have an observation. For example, it is 0 to 100. Now it's 30. So you use 30 divided by max minus mean, which is 100 minus 0. So that 30 divided by 100 is equal to 0.3. So for all of the observations, you do this. It's called normalization. The second way is called standardization. First, you subtract the mean value so that standardized value always have a 0 mean, and then divide it by the standard deviation so that the resulting distribution has a unit variance. So the other way would be you do some sort of standardization of the variable so that you can use the standardized variable to run through in your model. So that's the second way of feature scaling. Okay, I'll stop here for the first part on end-to-end machine learning project. And in next section, I'll follow through the rest of the steps. Thank you.